Okay, finding bugs. That's the fun part, right? That's what we do all day long. Apparently, I heard a new thing that you discovered, I think it's infra, that you could check in code which doesn't compile. Is it true? Ah, this is good. There's existence proofs, and you could ship. No, oh shucks. If you figure out how to do that, let me know. Okay, use of undeclared identifier comparison. Counts comparison. So we go and I thought we declared it, right? No, here it's all right. It's not identifier. It's in, that was in line, instrumented line 50. So let us go to instrumented line 50 and anybody sees where line numbers are? Why don't I see line numbers? It's not movable. Could do it. Yeah, he has a mouse. Oh, thank you. So comparison, it says it doesn't know, but I was positive. Construction equality comparison. Comparison and a line. No. Comparison. So why doesn't it work? No. I couldn't. Look.
You don't have it in your CPP, right?
Plus. What was the name of the file? Count operations.cpp. What was the other one? .cpp. Okay, so we know that it used to compile, and now it doesn't compile. So we could say diff, what is it? Instrumented dot h with dot lecture 3. That will show you what happens when you improvise. Instrumented.h. So the only
When you created a class.
no. What I do not understand what happened, guys. With pipe into more. You know, your sounds very cool. Yes. Algorithm I don't need. C standard def. That I do need. Okay, so let us try. So, okay. You say that what I miss. What did you say I miss? Anil, remind me, please. Yes, that's what you claim I miss. Yes, and I do. But that shouldn't matter, you know. Yes, but let us still look at more. Initialize size N. 8 becomes 7. I don't need to name it. Let us this is good. So how do we go? What is the difference anybody sees? I do not. Yes, in one place I use object, another place I use value, but that's all right. Okay, so let us try clang plus plus. What was the name? Counted. No, I'm in the wrong directory. By the way, I need to probably commit it and push it, yes? So that you guys could see it. Right? Or but let me try fixing it. So clang whatever plus plus no member named field. And I did not include it. That would be nice, but okay, guys. So that means I need to go to here and include. If it's the only bug, guys, it would be really nice. Include algorithm. That's where we need to include it. Everybody follows what's going on? Control X, Control S, and we go back, and we attempt to compile. This is good. Let us compile it one more time, but with 03. 03. Okay. So just to show that it actually works, something works. Yes?
Can we go to the instrumented.cpp, please?
Absolutely. Can we go there? Yeah.
So in the function initialize, you use parameter n, and n is also a name of one of the enum variables. This is a confusion in my mind. And then you also you rely on the fact that n has a value 0.
Would that help?
Yes, if you use counts n, not counts 0. In the beginning of this line.
Yeah, I guess. Then, believe it or not, I have to do, if you want to do it this way, which makes sense, since I asked for it by using enums. Let us then go to and do counts plus n.
And then counts plus n plus number of.
I agree. I agree. Well, of course, the sad thing that you know and I know that n is 0, but for this particular thing, I buy that.
So wouldn't it be then easier to, in the definition of enum, to say n equals 0?
Wouldn't it be? It's not, again, I think that the idiomatic use of enum, sort of, when it's you do not depend on the mapping, sort of. So this is again, let me show you again the last message from this exchange between Bjarne and me as of yesterday. So Bjarne says, I'm teaching a course. What is it stuff? Machine is good, pointers are good, C is good, C++ is much better, stuff like that. But enums are double plus ungood, says Bjarne. And whatever. And I answer, enums are work for the future generations. I still do not know what they really are. They are not types. I know they are in C++. They are not containers. I do not know how to extend enums to floating point types, etc. There are little that is ungood in C++. At worst, there are honest attempts to solve real problems. Valeray is, however, ungood. This is an in-joke. There is a part of C++ which is beyond redemption. That's Valeray. Whatever. So enum is something which is shaky, right? In general, it's not an easy thing. It's not a natural thing you have. And I find, sort of, for whatever it's worth, this is sort of all right. I wouldn't do what you did with adding n, but since you insist, no, I understand your point. That's what I mean. This is this funny thing. I don't want, of course, here to write n is 0, copy 1, assignment 2. I rely implicitly, of course. None of my code would work if it is not so.
But if you're indexing an array with these enums, then the only thing you should probably rely on is n being 0, and then the rest being like n. So you don't say n equals 0.
The standard guarantees the behavior that we have. So
It's not, this is, again, we're using a very shaky language mechanism, and we use it as idiomatically as I know how. But this is not something which I could defend. I'm just explaining. You observed that I have very strong opinions about, say, how to write constructors or how equality works. What's the meaning of equality? Here, where I am on much shakier ground, I do not know. I literally, this is, yes?
the only possible defense is that the standard says that works.
Yeah, but it's not good enough for me, right? Sort of, because, I do not, sadly enough, I do not view standard as something which written in stone and comes from some mountain. I know the people who wrote it. and that sort of moderates my enthusiastic acceptance. So, right? You're right in a sense. This is why I wrote what I wrote, and I'm somewhat uncomfortable with this n. I'll get rid of it. However, I buy the argument that I shouldn't use. Yeah. Let,
So maybe the second, this first n is also not needed because n could be in any position this array, and then this code will work.
this is. You see, neither you nor I really know. I'm just saying, and this is why I put it in. First of all, this base class where I put all kind of junk stuff, and then this I put into .cpp, which is sort of truly implementation detail. So eventually, sadly enough, my idea that everything should be just so perfect works 98% of the time. But then there are 2% where you really just say, well, I no longer can just be absolutely right. So we change. So it probably works now. We have to, there is another golden rule. What's the golden rule? Yes, because one thing I learned, that I cannot make any change in the code without introducing a bug. I've been programming now for over 40 years, professionally, full-time. I still could change just one character and it stops working. There are better programmers than I am who could do things like that, but I haven't met them.
So the last column is conversions, right?
No. We didn't change the stuff. The stuff is still I do not understand why it doesn't print. I no longer remember. Maybe if we do this, let me try. If we do operations normalized, we will start working on it in a second. After does it work? Yes, so here I print and it's like, tells you. Yes. There is, what happened? No. I think I got it totally wrong. No. What is, let me. How do I construct? Yeah, we do not do any constructions as I predicted. We do not because let us see what we do. We are sorting the stuff. Sorting doesn't do any constructions of underlying T. It doesn't know about underlying T.
Even that little code that calls iota and fills it in. When I was doing this exercise, it was calling my conversion routine.
Iota is not, okay. Let us look, okay. Now I need somebody, Anil, could you help me please? You need to help me to type in correct Git incantation. I know that you know how. Well, first of all, I need to get back to a screen I could read. Anybody knows how to do that? I lost my everything. And say Q. Yes, thank you. So I need to say git commit -a -m. Yes. Lecture 3. That works? I'm trying so that you could see it. Yes? Git push, yes. Guys, you're welcome to start working on it. So let us try. You have to go get to this directory, and now let us try to do some experiments. So we could count number of operations, yes? So let us, the simple assignment which you need to try to do is there are several sorting routines in STL. Anybody knows what are sorting routines in STL? Different. There is std sort, yes? Sorts. What other sorts are in STL? Anybody knows? Stable sort, very good. std stable sort. What does it mean? We will study it in more details later. What does it mean the sort is stable? Anybody knows? Very good. It does not change order. For example, if you sort things alphabetically and then stably sort them by department, people will remain alphabetically sorted within every department. If you just sort them with arbitrary sort, it will be all over the place, right? So there is another thing. There is another sort, partial sort. And you could use partial sort as a complete sort, because what's the interface to partial sort? 3 iterators. And what does it do? Anybody know? I mean, yeah, it's partially sort. What does it mean, partially sort? At least try to guess, guys. Yes, that's very good. So, what, for example, you give it 100 elements, and you sort from first to the 10th to the last. So what will happen?
First 10 elements will be in sorted order, but there's no guarantee on the last 90 elements.
There will be last 90 elements. There is a guarantee in some order. If you see what I mean, that is very often. Some of you might be familiar, people who work on things like search, that you don't really need to sort everything. You need to sort just a little bit. So that's what it does. But if you could sort a little bit, then you could sort everything. How would you sort everything with the help of partial sort?
Just set the third argument the same as the second.
Well, set the second argument the same as the third. That is the correct way of thinking. Of course, you are right. I mean, you move, then it will sort everything. By the way, simple test on what you remember from your algorithms classes. Guess what kind of algorithms STL uses for these 3 things? Sort is quicksort. Why is it using quicksort? Because it's quick sort. Yeah. We'll be talking a lot about quicksort. It's a wonderful algorithm. But is it stable? No, it's not stable. It's very unfortunate. So to be stable, what do you use? Merge sort. And what do you use for partial sort? Which is, by the way, you will tell me the answer, and then I'll tell you that it's wrong. I mean, meaning the solution in STL, which was good solution in 1994, is a bad solution in 2013. Yes, it uses heap sort, of course. And that's what algorithm books tells you. And that's what I believed was the correct solution. And it was a correct solution in 1993. Computers changed. Right? The algorithms which worked perfectly wonderfully in 1993 still work perfectly wonderfully in the books. But they don't work, as we shall see, in the computers. And we shall see that there is a perfectly wonderful 3-line solution which we could change partial sort. We'll re-implement partial sort in this course and make it much more acceptable to modern computers. But it's not the standard. The implementers of the standard library will take them another 15 years to catch up. So, okay, so let us do the following exercise right now. You have everything. Try to compare number of operations between std sort, std stable sort, and std partial sort.
Can you print the first line of your output? Can you show us the first line of your output to make sure I'm getting the same counts you're getting?
Yeah.
You have the normalized one.
Yeah, it's the same, that normalized version. Let me explain why normalized version is more important. Because normalized version tells you that if you're given n elements, or actually in this case, if you're given n elements, how many operations you do per n log n. Because we know what is the symptotic complexity of these algorithms. It's n log n, right? So what we want to establish is the operation counts for every n log n. Because those of you who remember reading Knuth, you all should nod your head, even if you do not remember reading Knuth. In the beginning of the first volume, when he introduces complexity, he says that how do we measure complexity? And he tells you, we measure it as a function where we have these different coefficients for different operations. So many of this, so many of this, so many of this, and so many of this. And this gives you literally precisely that thing. It says that if you sort with this sorting algorithm, your complexity is going to be the cost of copy times these coefficients, time n log n, the cost of assignment times 1.3 times n log n, the cost of, and so on. Right? So in some sense, this thing should allow us to predict timing. As we will learn later, nothing of the sort is true. So whatever Knuth believed when he wrote first volume, which he did 3 times at least, is no longer true. Right? Because what we will discover that computers got very strange. They actually often do many operations in the same cycle. Right? So very often what we will observe is that we could do more operations without actually incurring more time. But that's far away in the course. First, we need to learn to deal with that. So you have to go and look at the code now. This is, I shouldn't be talking. You should try to figure out how to write this thing normalized or unnormalized with different sorting algorithms. It is simple. If you have questions, ask. There are none already figured out. You will answer.
My question is, I suspect the counts I am getting are not the counts you are getting, which I find mystifying because I started from the same singleton class.
Compare the code. I mean, my code could have bugs. Your code could have bugs. So we have to figure out. You want me to run the one without normalized? Sure. How does it go? Count operation. This one? This. And then this. So the same numbers?
I'm off by 1 in copy.
How could we off 1?
Well, I don't have your instrumented.
And you're off just only by 1. That's very interesting. That might be my bug.
Off by 4 in assignment. Off by 3 in less.
And 1 in destruct. Guys, that's a great mystery. We have to find out. We have to find. Which standard library I'm using? Whatever comes from Clang. It doesn't matter. They're all the same. As far I'm not using any standard library. Okay, let me demonstrate. Let me just recompile that. I cannot I cannot change to Linux simply. But for this, I could do gladly. This is G++. Yeah. So, I mean, I think I get the same numbers. The actual sort function on your thing could be different. This is true. This is true. Very good point. So I could fix that by bringing in. Okay, why don't we do something very, very simple? Well, by the way, just do experiments. Let's find the numbers. You got all the numbers? Are they the same?
No, I mean comparing two sorts.
3 sorts. So let me go and look at. Why is it not working? Control X, Control F, count operations dot cpp. Control S, Control F. Hernan, let's do the following. Let's both of us try to do stable sort. You see what we need to do? And compare numbers. Control. So the stable sort functor. So I just need to put word stable here. Ready? Okay, I'm not ready. I'll be ready in 1 sec. Okay, no, where is it? Okay, so what I need to do, I just need to recompile this. And then I need to run this. These are my numbers.
I'm getting 1 additional copy. I'm getting 4 fewer assignments and 2 fewer less.
Anybody is doing it on the Mac?
Is anybody doing it on Linux? I'm getting my numbers.
Yeah, no. This is very interesting. Yes. So what it shows, what did we just find out? We just found out something interesting. What did we find? The algorithms are different. You see, I always assume, of course, being the guy who did all of that, that it's the same algorithm wherever I go. But of course they're not. I wrote something 20 years ago. Obviously, somebody modified them a little bit over these 20 years. So people at Apple did something slightly different from people at GNU.
You're saying they're modifying the STL code?
How else would you explain it?
So what version of the STL libraries are on both systems?
Yeah.
There is no such thing.
There would be version numbers of the installed packages on.
Yeah, there's some version, but these are different code bases. The question it's like, anybody runs Windows? Here? Yeah, but he has Linux numbers. And
Your numbers match his Linux numbers?
What is, okay, did you try stable sort? What are your numbers for copy at the first? 37.
90 assignments, 37 destructors, 51 comparisons.
Yeah, that's exactly what I get.
So it's a slightly different code base. And actually, I cannot even tell you how, I mean, this is something which sort of tells you that the algorithms which you assume are the same are not the same. And if we slide down, let's go to the last line. How much is the difference there? The last line here.
It's 1,000 copies, differences in copies.
1,000 copies,
More like
1,500
1,500.
more, 1,500 less.
1,500 less. No, sorry.
It's 3 to 5, 6 to 1.
3 to 5 means less.
It's like 500.
500 less, sorry.
500 less. Okay. And assignments?
1,000 more, like 900 more.
Okay. Let's try, guys. Let's try partial sort. Well, I need help. How do I try partial sort? Anybody knows? I implement the sort functor. Yes, that's a good idea. And how do I implement the sort functor? Yes, that's a good plan. Let us see. Y. And we call it heap sort functor, because it's not going to be partial sort, if you think what I'm saying. Heap sort functor, and it is blah, 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 blah. Anybody could help me here? Partial sort, first, last, last. Everybody agrees? Let us see if we figure out how they differ. I have to go back to this guy, and I have to say heap sort, yes? Control X, Control S. So we're switching. And now what do? We go to, now we go to here, and we say Q, and we say okay? Yes. Two.
The code hasn't been uploaded correctly. We only get the last.
Oh, yes. I will gladly upload. I thought you were making changes in parallel, but you shouldn't, yes. Where is it? Why am I not? Commit, no, git, yes. Commit, git status, gladly. No, they're all there. Or instrumented is not added. I apologize, guys. You should have told me. So what were you doing? And those, I apologize, guys. I'm just git add instrumented star. You don't need to have heap sort. You use partial sort. Partial sort. Remember, we talked about it. just a second ago. Let me show. Okay. Anil, this is how we did it. This is how we did it. We went here and we defined heap sort functor. Right now, if I say std partial sort, we're relying on the fact that that's how it is implemented. It shouldn't be, but I think it is. But in the meanwhile, let us, before we're done, I would like to put us in a good situation. So what I need to do is to say git commit, now pushes too early. Git commit minus a, no, I have to, no, a dot out is not checked, so it's all right. Git commit minus a minus, what is m? Final lecture 3. Okay, some of you might want to do a little work at home. Some of you. If you don't, doesn't matter. What would be nice, it's right now we have a framework for, we have several algorithms, at least 3, right? And we could measure operations, so you could just play measuring operations. But more importantly, you could attempt to do with our measuring thing a simple thing, which Ahmed already did. I don't know whether you remember his message. He said he changed it. Right now, we pass as an argument to it. If we go to this count operation CPP, it takes a functor which specifies what kind of sort it is. Yes? And you could figure out what's the technology by just looking at the code. We pass this functor, which sort of an amazing thing. We will study what functors are one of these days, not today. But Ahmed proposed to pass another functor. Right now, we generate input by doing iota and then randomly shuffling. But he correctly observed that there are very different inputs we might want to use. So we actually want to have 2 functors. One functor which we do not measure. We don't care about how many operations it does, but we measure what is the shape of the input. All right? So the task for you is to try, if you would, I just think it's an interesting task, to figure out how to pass that, and then figure out what are interesting shapes for the input, and then running these algorithms and see how different shapes affect the performance, yes? And let us just talk a little bit about possible input shapes. The one which we are using right now is the most basic one. It's uniformly random sort of input. It's good, but it's not enough. Sort of there are shapes. Let me just tell you in general about shapes. There are some useful shape which is this. Things are already sorted. You say, why would we want to see how good sort is for already sorted data? Well, as we'll discover later on, some sorting algorithms are particularly bad for this particular configuration. And if we have this, what we also should have? We should have the other way. And then let us think about what other interesting shapes are there. The other interesting shape is constant, of course, but also a valley shape, up and down, and hill shape. Down and up, and hill shape, up and down. And shape like that, and shape like this. And then finally, if you do that, I'm not saying by next week you could do that, but eventually if we learn to sort of measure things, we need to learn about shapes of input. So let me just mention. Right now we assume that all the elements are equal. And is it good? Oh, it's neither good nor bad. It's just they're all, pardon me, none of the elements are equal. We need to also eventually put a measure, and for all these shapes to have sort of like they go like that, right? Some ratio of how many equal elements are there. And then finally, in terms of distribution, random shuffle of uniform shuffle of random data is very good, but it's not very realistic. A distribution which is very, very common in real life, which we will study, but again, I'll just mention now in case somebody wants, like Ahmed will try to go ahead and implement them all. There is a very interesting distribution which happens in real life called Zipfian distribution. There's a guy called Zipf, and according to everybody, the world is ruled by Zipf. So what is Zipfian distribution? Anybody knows? Okay, it's, simply speaking, it's, let me describe it incorrectly and then I describe it correctly. Sort of, let us assume that the most probable guy comes with probability 1. You say, no, it's not very interesting. The second most probable guy comes with probability 1 over half, and the third most probable guy comes with probability 1 over third, and the fourth, right, harmonic series. Of course, that wouldn't work because they all need to add up to 1. So what do? You normalize. So the guy number I comes with probability 1 over I divided by natural log, by the sum of the harmonic series up to n. Those of you who remember, it's actually natural log of n plus something called Stirling number, whatever. But you could ignore it. You could just assume that it's, roughly speaking, natural log of n. You remember what natural log is? See, math strikes again. So, yeah. Okay, see you 2 weeks from today. 2 weeks. So you have 2 weeks to study Zipf and stuff.